Okay, so we're going to talk about sheet metal processes today, since we kind of skipped over those because of the way that the schedule worked. But before we talk about sheet metal processes, we should talk about the final exam. So the final exam is a take-home exam. You will get it on Thursday in class, or it will actually be online on Thursday in class. For the take-home exam, you are allowed to use your notes and you are allowed to use the Canvas site, nothing else. So those two will be on there, and then there's a place that you will sign that you used only the notes in the Canvas site and didn't talk to your peers and didn't use any of the rest of the interwebs. There are, let's see, your final exam time is from 8 to 10 a.m. on Tuesday. So it's going to be due Tuesday night at 5 o'clock probably, so that you can work on it whenever you want between Thursday and Tuesday night at 5 o'clock. If you want to, you can just work on it during the 2 hours that you would normally be in here in an exam. But you will see it on Thursday. I will talk about it, talk about the whole thing, so that even though you're maybe not working on it, you know, it can sit there in the back of your mind and you can think about good answers. There will be 2 options for the final exam, and you can choose what you want to do. So this starts with a story. One time when I was at Sandia National Laboratories, we had an internal research and development funding program that you could apply for every year. It was super competitive, very, very hard. You're applying against all of the rest of the people at the lab, and to be at the lab, everybody who was there had gotten, essentially everybody there had a 4.0 in undergrad, a 4.0 in grad, and better than a 3.8 in their PhD. If you were below that, they would not hire you. They spent forever badgering me about one class that I dropped in my undergrad, which was like 8 years before. Anyway, it was really funny in an odd sort of way. But so you're applying against these people who are super high caliber, really, really hard to get these things. When you did them, you would file a 1-page paper proposal. If that got selected to go to the next round, then you would write a 10-page proposal. Along with that 10-page proposal, you also had to submit a 2-page version of the proposal that could be public. So it couldn't have any classified information, and it couldn't have any IP in it. And so it kind of was a fluffy description of it. And then you also had to turn in a 1-paragraph version that could be used if it got selected. Then they would publish this set of what got selected for the year, and that had to go to Congress because that was ultimately where most of our money came from. If you got selected for that, then you would have to go give a presentation, and so you had to take the same information and produce it again in a presentation. So in all of this, one year we got frustrated with the whole process of writing the same proposal like 8 times. And so we decided to write it as a haiku. And it was just kind of a challenge to see if you could write the idea of your presentation in a haiku well enough so that other people could understand it. And so, if you remember, haiku is sort of 5 syllables, 7 syllables, 5 syllables, and it sort of starts with an idea, it builds tension in the idea, there's some problem, and then the last line kind of resolves that problem-ish. And so we did that, and it actually helped us to win the proposal, because we developed this idea down into a haiku, and we actually presented it in the presentation, and that caused the people who were evaluating it to remember it. and to understand it really well. So you have the opportunity to do one of two things. In both tests, you will do one problem that is sort of a wrap-up of a lot of the quarter. And so it is something that you're all familiar with, and how would you decide when to use chip forming and non-chip forming processes on it? When would you decide to use non-traditional or the non-traditional processes? How would you decide when to do things like casting or forging or any of those to create this device? So it's sort of think about the entire quarter and put it together. There's one question that is sort of an application kind of question that is more about your being able to think about what you've learned and think about what you might do, and to put those two together. And then you have an opportunity. Opportunity number one is to write 2 more paragraphs. It's like a page or a page and a half for those 2 paragraphs, and it's 2 questions where you're talking about 2 of the topics from the end of the year. The other option is to write 3 haiku. And those 3 haiku, one of them will be about the non-traditional or non-chip forming process that your group presented on. Or you could choose one of the other ones if you preferred. One of them will be about welding, and then the last one has to be about a metal forming or a metal machining process of some kind. So you can either write the 2 paragraphs or you can write the 3 haiku. All right? Any questions about that?
Does anybody ever write the 2 paragraphs?
Absolutely. It's easier. I mean, to write 3 good haiku is not easy, because you have to think about it. You're forming amounts of syllables. It's not just throwing something down on the page. That won't quite get you there. It needs to have thought to it. Yeah.
Will we be graded on the haikus according to a standard of like haiku writing?
No.
Are we graded on our prose?
Mostly what I'm looking for in the haiku, it's just a fun way to pull it together. What I'm looking for in the haiku is that it demonstrates that you understand the process. So I'm looking at it from a metal manufacturing kind of standpoint, and if it's not exactly 575, that's okay. Yeah.
So is a haiku like 3 lines?
3 lines generally.
Okay.
Yeah. Yeah.
Cool.
And you can look up haikus in the meantime to have an idea of if you want to do it or not. Yeah.
Can we try it? Like send it to you and like, is this total fluff?
No.
Okay.
You can.
I just haven't written a haiku since like.
Go to
I know.
Do you have like an example haiku?
I will try to find the one that I wrote for that presentation, but I'm not sure I can. That was a long time ago when dinosaurs roamed the earth. I can probably show you one from last year.
Can we ask the writing center, or if we write one down before the test, ever like paid writing center?
No, you just because what I really want, it's not really about the haiku, right?
Okay, it's about understanding.
It's really about showing your understanding of the process. So make sure that it demonstrates an understanding of the process, probably a deeper understanding of the process than you had before the class.
And the 3 haikus were the process that we presented on, welding, and that, what was the last one again?
It will be something about a metal manufacturing process. Open for you to choose. And the 2 paragraphs are totally reasonable as well. So they're actually easier to grade, though it takes longer. All right? So we'll go over it in class on Thursday, along with the world famous manufacturing challenge and the class evaluations. There we go. Any questions? Yes.
Will the test be the kind where like you open it and then you have 2 hours from that moment? Or
No, it is just a test. I am suggesting that you spend between 1.5 and 3 hours doing it. If you're past that, you're spending too long on it. It's meant to be a 2-hour test at most. There are kind of guidelines on the length of the things to write that are on the test. Yeah, but it is not a, you open it and the timer starts and it's gonna shut you out at 1 hour and 59 minutes. Yeah, it isn't. Yeah, you can do it whenever. Yep.
What are you doing for lab today?
What are we doing for lab today?
Clean up.
It is lab cleanup day, and then after you've done lab cleanup, you will earn your bearing and your thumb buttons, and so you can press the bearing into your spinner, put the thumb buttons on it, and then you can take it with you. Okay.
Can I schedule a different time to do it?
Anything else?
Grind the stands that we cast.
Oh, that's an interesting question.
Wait, what was the question?
I'll look and see. That's a, yeah, good thought. Forgot about those stands. I'm not sure if we had enough work, but maybe we did.
So that we can do it really well. You put them on the machines for so it's easy to, there's just like a platform for the fidget spinner to quickly sit on. But if we had them, then we could display them.
All right. So we're going to talk about sheet forming processes. So sheet forming is normally it would come immediately after talking about bulk forming. So if you remember in bulk forming processes, we were forging and we were rolling and we were doing these big things with big machines, squashing metal to make it a different shape. The sheet forming processes are a secondary process. So it's after you've already rolled the material out and it's relatively thin, and then you're going to do something to it. And these are things that are pretty unique to, well, not unique. Anyway, never mind. There are things that are pretty cool that you can do to it that are because it's metal. So you could not do these with paper, right? You couldn't take paper and reform it to just sort of pull it into a wild shape like any one of these because the paper would wrinkle. And you can do this with plastic, right? You can thermoform it, you can vacuum form it, things like that, where you can pull it over a shape. And but similarly to metal, as with plastic, if you're doing too big a change too fast, you can get big wrinkles in it at certain locations. And so understanding how to do this process is, it's pretty cool to be able to do that. So lower forces, lighter machinery, easier to do. Typically in the plane stress region, so it will be somewhere between plane stress at 1.15 sigma F and shear at 0.7. And often one of the things that we're dealing with is that the material may only be a few grains thick. So the grain structure may be all over the top if you're looking at a big sheet of material, but the thickness may only be a few grains thick. And so we run into some real challenges with that because as we're trying to work with it, individual grains making a big change will have a big effect on it. Whereas normally with a large piece of material, if an individual grain changes, it doesn't affect the bulk very much. It just happens. Okay, there are 3 major categories that we're going to deal with. Shearing, which is cutting or cutting the material, bending, and then drawing or stretching, which are the cool things that you can do at the end. There are lots of weird stuff that you end up dealing with when you're dealing with sheet metal. One of them is that as we get this thing called yield point elongation, and this happens because of the fact that the material is so thin. So it will yield in one little tiny location, and then that strength hardens right there. And then it will yield in the little bit of material that's right next to it, and then it will yield in the little bit of material that's right next to it. So rather than yielding uniformly as a bulk, it sort of does it in little steps. And if you look at a graph of material that you're testing in a stress strain test, you'll see this really long yield point as all of the little adjacent areas yield. And so it's kind of an odd thing. It doesn't matter a whole lot except that you can visually see it on the material. So you can see, like this image, where it's really a different color here in the middle, or this one where it has these different colors that are on it. Visually it's very unpleasing, unhappy, something, I don't know what it is. But anyway, we have to deal with that. So the answer to how do you deal with it is you cross-roll the material right before you use it. So you roll it in one direction, you turn it 90 degrees, you roll it in the other direction, and then you use it pretty quickly. And it's actually, it is a time before everything settles back in, so often you want to use it within like an hour or so of doing that cross-rolling. We have to deal with anisotropy, especially with rolled material. It will, because the grains are elongated, it reacts totally differently in one direction than it does in the crossward direction. And so we have to deal with that. One way is to cross-roll it before we use it. Otherwise, we can just know that it's going to act very differently in the two different directions, and we can make it happen. The grains, like I said, it may only be a few grains thick. It is a lot easier to do this process if it is as many grains thick as you can get. And so having the smallest grains possible helps you out in all of the metal processes, the sheet metal processes. We end up with a lot of residual stress in the parts, not different than anything else we do in metal. We have that opportunity. And so we may have to do some heat treatment or just know that the part may warp at the end. And then we have spring back. So you're very used to spring back. If you bend metal, or especially sheet metal, you bend the metal and you let go, it will bend back some. And it's just the elastic stress releasing. And so we have to plan for that, and we have to be ready for that to happen. So we overbend the metal so that when we let go, it will bend back to the place that we need it to be. And then the last one is wrinkling, which is, as one would expect. You have too much material as you try to fold it over something, and so you have to go slowly and work the material out and allow it time to deform such that it doesn't just wrinkle instead. So the first process is shearing. When we're shearing something, we will have two sides that cut against each other. It may be that we have a punch and a die, and the punch punches through the die and punches out a piece of material. So they are not Pringles. It's a real downer, isn't it? So anyway, we have a punch and a die. You can punch through there and it will punch out, well actually, punch in the die. It will punch through there and it will punch out the shape that you're expecting it to make, hopefully. This is a pretty quick method of making common size or common shapes. You can also do this with a roller or with something like shears. And so scissors are a shearing process, right? You have one blade of the sciz. Is it a sciz and a, I don't know what the two blades are anyway. So you have the two, why is it a pair of scissors? I don't know, anyway. You have the one side. Yeah, people sometimes say a pair of scissors.
Yeah, but each one is a scissor. There's one scissor and two scissors. And together they are.
But I don't think that they are individual scissors. It's just anyway. You have two blades. One of them is acting as the die. The other is acting as the punch, and it rolls past it and it cuts whatever you're cutting. You can do that with a set of what is called shears as well, which essentially look like a big set of scissors. When you do that, a couple interesting things happen. At first, as the punch moves through, the material gets rolled over and it gets burnished, which is kind of polished smooth. and the material will be smooth at this top edge, and it will go until you generate enough stress between the corner that you're cutting and the corner of the die, and then all of a sudden the material will crack and it will ductily fail, and it leaves a rough edge. And so you can tell if a part, often you can tell if a part has been sheared, because when you look at the edge, it will have a section that is bright and burnished, and then a section that is rough. And so if you look at these, you can see that that's happened, but looking at them, you also see something very interesting about these. On two sides, opposite sides, it is burnished on one edge, and on the other two sides, it is burnished on the opposite edge. And I don't know exactly why that happens. I don't know why this punch, I didn't get to see this punch punching them. I just asked if I could pick up some of the trash when I was at Woodstone, and they said I could. And so I did, and it's got those little corners on it. So anyway, the rest of that is a pizza oven somewhere. It's pretty cool. The amount of space that you have between the punch and the die is called the clearance. And if you have a really small clearance, so it's really tight, then you get a really good looking part, and it will be burnished all the way down. That's a process called fine blanking. But to do fine blanking, you have to have a very precise machine that can line up the punch and the die really well. It also increases the force a lot. So the force of fine blanking versus the force of shearing will be much, much, much higher. Now, 40% more force, according to that slide, so it must be true. And so you don't always want to do that, because sometimes you don't care so much about the edge, or you're going to do something afterwards with the edge. And so then it is a lot easier to have more clearance, because your machine doesn't have to have as high a tolerances on it. There are a lot of shearing operations. You don't need to write these down. This is just for you to know that all of these odd names are shearing operations. So slitting, blanking, piercing, lancing, perforating, notching, nibbling, trimming, shaving, dinking, fine blanking are the whole list of odd names applied to shearing operations. And they all are different ways coming in, cutting from the edge, or punching something out of the middle. A little bit different processes, but overall sort of the same thing in each one. There's an interesting thing that happens. It's interesting just to me, but anyway, that's fine. I can deal with that. The punch that goes with that one. Anyway, if I am trying to punch something out, and it turns out that the force is too high, and I can't punch it out because I don't have enough ability to apply that much force, one thing that I can do is I can angle the edge that I'm punching with so that it sort of focuses the load. So instead of punching with a punch that's straight across, I can punch with a punch that has an angle on it. That will focus the load here first, and then partway through the load will be focused here, and it will just move across. Now, when you do this, the load is a lot lower, but the amount of energy that it takes to shear the material is exactly the same. And that makes a lot of sense. It takes an amount of energy to shear the material, and so no matter how you do it, it's going to take that much energy. You just spread it out over time. So that's something to know. And that's why scissors, right? As they come down, you aren't just shearing it straight off, because that would be pretty hard to do. There are machines that do that, like we have one down in the lab. And when you're trying to shear metal with that one, does it all at the same time, so it's got a huge rail across it, and you step on it, and it takes all of your body weight to be able to shear through a piece of metal. But at the same time, I can take that same piece of metal and I can cut it by hand with a set of hand shears, because they focus that load at just one point and they sizz across it. I don't think sizz is really a word, but we should make sizz be a word. Okay. Other things I can do. We just have 2 slides of bending and then we'll go to the big machines. We can bend the material. So when we bend it, we are dealing with spring back, and we are dealing with thinning, and we are dealing with a change in length. So when I bend the material, the strength of metal, the compressive strength, and remember compressive strength is kind of an iffy term overall, but we will find that the material is a little bit stronger in compression than it is in tension. And this is true of most materials. So what happens is, as I bend the piece of material, it will get thinner. And the reason that it gets thinner is because this inside compressive edge does not change length. It stays the length that it was before the bend, and the other side stretches out. Now that wouldn't have to have happened. If the compressive strength was lower than the tensile strength, when I bent it, the part actually would have gotten shorter and the inside material would have kind of glommed together and it would have gotten thicker. But that's not what happens with most materials. And so this gives me 3 problems when I'm bending the material. The length changed. So if I want it to have certain dimensions at the end, I have to be able to predict how much the length is going to change. It got thinner on the corners, so if I needed to have a certain thickness of material, I might have to make the whole part thicker than I planned so that the corners would have the same strength that I needed. And then spring back. So I bend it, and the angle to which I bend it, if I just let go, it will open back up and it won't stay where I put it. So I have to overbend it and then let it go back to the position where I wanted it to be, unless I use materials that have very small amount of spring back. So generally that's a material that's pretty soft. So that the other thing that I can do is I can adjust the radius at which I bend. So if I bend at a very tight radius, I will have less spring back than if I bend at a very large radius. Okay? Oddly, the machine for bending is called a brake. It's just the way it is. Somebody named it, they didn't ask us. When we're bending, this is a place that we have a real issue with the grain structure of the material. If the material was rolled and it flattened out all the grains and lengthened them along the direction that it was rolling, if I bend it across that, the material will get all these little cracks in it. And so I always want to bend at an angle to the direction it was rolled, unless right before I bend it, I roll it in both directions to try to equalize the size and the shape of the grains just before I use it. And so when we plan these things, if we have an opportunity, we would roll the material and we would do all of our bends at a 45-degree angle, because that way we don't have a preferential direction. It means that all of our bends are equally good or equally bad. So if we can do it, we do that. This is just a note, because every lecture should have a picture of a stress egg. We are primarily, for shearing, living right here in this area at the 0.7 times the flow stress. And we sometimes get down here to 1.15, but we're generally in this length except for drawing, which we'll get to in a few minutes. So we're living right there. That's kind of nice. That means it doesn't take much force to be able to deform the material if we're cutting it and if we're shearing it. So that's exciting. So in one of the most repetitive manufacturing music of the quarter, I think this one probably wins that award, but also pretty darn cool. So this is a machine. This is a CNC bender, and its purpose is to make, to punch out and to shear metal parts that will be needed. And so it has shears and roller shears and benders, and is pretty crazy to watch it work. So what I want you to watch in this and to think of is what are efficiencies in this process and what are inefficiencies in this process using this machine to do it. And I don't know what it's making. It's they look like electronics housings of some kind. You'll be tired of it. So that's installing the punches. The punch is the top half, the die is the bottom half. So it's still using a punch and a die. There's a really sweet controller using Windows. You'll be tired of it in just a minute. Just wait. I don't know. Yes. Too long for the music. So it has little tools that help position it and hold it in the right place. efficiencies and inefficiencies that you see in that process? Kind of slow, in what way?
In what, like, you're making all these unique carts, which is really cool, but I don't know if you're trying to mass produce this using this one machine.
Okay.
It doesn't seem as mass producible.
Yeah, so it's hitting a specific window because there's a lot of customization in these parts. But if you wanted to just produce the whole thing, there's a way to just chunk produce the whole thing. Yeah.
It eliminates human labor like almost entirely. Like all these would have to be, like someone would have to bend it and then someone would have to punch it. And if you were doing it by hand, it would be separate things that you'd have to do.
Yeah.
So that's cool.
Okay, so the person only had to pull it against the dowel pin at the beginning and put the sheet of paper or sheet of metal on the bed. And somebody ostensibly had to program it and figure out how to do it, which I think would be really hard. Because once it gets floppy like this, getting it to still move around and not get caught on things would be really tough. And it's weird, right? It started in that front corner, and that makes a lot of sense to me, that you would start up there and have those parts falling out first. But then they came to this back corner, so there's some process planning voodoo magic going on here that they know that we don't. Anyway, yeah.
It seems to eject all the parts to the same place, even though the parts are clearly not the same. And
That's
so
true.
you have to have either a guy or a machine or whatever sorting,
Yes.
like,
That's right. They're all going in the same bucket at the bottom of the machine. And so somebody's gonna sort it. So that part of it is not automated. All right, what else is an efficiency or an inefficiency? Yeah.
I feel like the amount of tool changes could be seen as an inefficiency, because that takes time. Obviously, changing tools, you're not making money.
Yeah, that's right. So the tool changes are not very quick, and it had quite a few of them, and those tool changes have to be done in a very specific order because it has to go through the different parts of the process. And many of the features take 2, 3, 4 different tools to make them. Yeah. How about material usage? Yeah.
It's pretty limited to the thickness it can do.
Okay, yeah.
I don't see it doing much more than whatever that is, like 50 thou or something.
Yeah, so it probably is pretty limited on its material thickness, and limited in the punch strength. Yeah.
The fact that it can like punch out the stuff and like bend it up is pretty cool, because like if you're trying to mill it, you just start with this like way thicker piece and you have to take off like almost all the material.
Yeah, and so it is pretty cool for that because you can do all of this out of plane sort of stuff. Notice that all of the out of plane stuff has to be up. It all has to be in the same direction. So all of the part design now is different because you cannot displace anything down or it'll get caught on the system that moves things around. So anyway, that's a limitation of it. It's really good if you have an entire sheet's worth of material to make. If you need to make that many parts, it's really cool the way that they nested them in here and they're using the sheet pretty well. If you needed one part off the machine from one corner, it probably wouldn't work very well because then the next time you're trying to use it, it's got this floppy portion of the sheet that is got a big hole in it. Okay, so let's look at other ways that we could do this. Thanks. If we wanted to do the ka-chunk method and make it all at one time, or if we wanted to do higher volume, we could do a process of progressive dies. So in a progressive die, what happens is the parts have a ladder that feeds them through, and they move one station at a time from station to station. Each station does something different to the part because you have to shape it in order to get it to form completely without wrinkling. But this one machine goes through and makes the entire part all the way through. And so here is a guy talking about his progressive die.
So as a basic explanation, a progressive stamping die, progressive part, is going to be material that is fed through some kind of a feeder. In this case, we use a mechanical punch press. And the feeder is going to feed this material through progressions, a given distance, all the way through each station, and then at the end, we have a finished part that comes off the die. Inside of a progressive stamping die, we can do piercing, we can do trimming, we can do forming, we can do pointing, all kinds of different operations, and we can even have feeder bowls that introduce hardware being staked into a part. We can also do in-die tapping. All of these different things can happen while the press is going up and down. At the end, the parts are cut off. Once the strip is all the way fed through and we're running on automatic through a coil or a strip, every time the press comes closed, we are going to make a finished part, or finished parts that, in this case, this is a 2-off die, where we have 2 parts that are coming off the tool. We're looking at a part where we're doing some piercing, we're doing some trimming, we're doing coining, we have forming in these stations, we have a stamp that applies, and finally a part that's being cut off at the end. To start off, we're doing some round hole piercing. These 2 outside holes actually end up in the finished part. This center hole is called a pilot hole. The reason we have a pilot hole is because we need to know where this, we need to qualify where this parts are in the strip throughout the entire tool as it goes through the progression. So typically, we like to use a pilot that is not in the part for a couple of reasons. We don't want to damage the holes that are in the current part, and also by putting the pilot hole into the scrap web, we can use whatever size we want, whatever benefits for the type of part that we're making, as long as it doesn't increase the amount of scrap that we're using to make the part.
So that is a way to make a lot of different parts really quickly. It's pretty amazing to me that that works because it's just vertical motion. That's all you have in that machine is only vertical motion. And any other out of plane thing that you want to do, you have to figure out a way to make it happen with vertical motion. And so they're pretty ingenious when they do that. What is efficient about that process?
It's fast.
Okay, super fast, right? It was a couple seconds and a part gets spit out of the end of the machine. What's inefficient about the process?
It's a lot of force we need to do, 6 steps at once. You need a big press.
Yeah.
To make that happen.
So it's a big press to make it happen. You have to equalize the load along the press, so there will often be stations where nothing happens to the part, and that's just spreading out the work across the part so that it's all equal. All right? Yep.
Seems like the part would either have to be designed around the machine or the machine would have to be designed around one part.
I think it's both. Absolutely both. So you design the machine or you design the dies. So the big machine that goes up and down stays the same, but all the dies that are fixed to it are only for making one part. And if there's a design change, you have to remake all of those little sections. So it's not like the last machine where on a design change you could just change a little bit of code and it would do something totally different. This one is big changes in hardware. So it's fine.
So as
a lot, and not so good if you're making a few. So this is going the other direction. So ultimate flexibility, but more user interaction. Though this machine's pretty cool, so look for inefficiencies and efficiencies in this process as well. From the happy green shirted person, who likes to clean his gloves often. Typically after he touches the screen. Notice that there's that backstop behind it that actuates into place to position the part at the right location. Then he goes on to change the dies and do something else and make other parts. What do you think of that one? What's efficient and inefficient? Yep.
A lot of really versatile tooling, but you gotta know how to use it.
Okay, yeah, there's a lot more versatility to this, but you really have to know how to use it, and there's not a lot of help. So there was a help at the beginning for where to put each of those, each one of the dies and punches. And then after that, you know, knowing the order of which goes in there, how to orient the part, when to flip it over, all of that is up to the operator, yeah.
There's also a bunch of design intent that goes into the part with tabbing and how you're gonna set it up for like weld joints and stuff like that.
Yeah, that part folded up and the little tabs fit in little slots. It was all pretty cool when it got there.
Yeah.
This one does a lot thicker material, so not nearly the limitations that the others had, but clearly way slower. There's another video in here that we're not watching today, which has a robot doing the job of the green shirted person. So if you want to see a light robot do a green shirt person's job, there's one in there for that as well. This one only does bending. It doesn't do the cutting, but if you've already used a water jet or a shear or something to stamp out the parts and to get them to the right shape, this is an automated bender, and this includes a large Italian man. He does not look very happy. He's not a green shirt person, no. He does not.
Very serious, wow.
He has a scanner, and that appears to be his job. Scan the thing, load the machine, stand back.
Does he know? Depends on how much you get paid.
He might be the funniest person just because he's quiet. He might be an introvert, but
That's true.
you know, my grandmother was the quietest person, but if you were sitting next to her when something was going on, she would say these little things. Whoever was sitting next to her was just dying laughing all the time, but nobody else heard it, ever. He might be like that.
She's like whispering in the middle.
Yeah, sure. Hey, can you tell that the machine's laughing right now?
No, I can't. I don't know. You haven't talked about
No, because it's on the way down.
What do you think this part is?
It's a little box enclosure. When it gets to the end, it looks like an electronics enclosure, but the good ones are. I mean, that was pretty cool, the way that clicked into place and exactly closed up the end of the box. And this next one looks like a total disc. I don't know quite what's going on with this one. I'm assuming it has the next thing, because it's like, whoops, that was too tall. Oh well. Next time we'll do better.
I like the thing that jumps it over.
The thing that shelves it over seems totally outsized. It's enormous. Pushing this little box off the side. Okay, what was efficient and inefficient about that? Yep.
That was so slow.
Well, it was kinda slow, but if you try to bend something like that, I mean, if you compared it to the last one, if you had to set where the teeth were and put it in there and bend it, and then change where the teeth were and bend it,
Yeah,
it's
I guess
faster
so.
than that, but it is not fast at all. The adjustment of the bars in and out does seem incredibly slow for what it's doing. All right, what else is good? Yeah.
Seems like a perfect way to make like computer cases and get rid of manual labor.
Yeah, so I think it's really good for that. The white shirted man, we did not see him. I don't know what he's doing, but he might be off playing pickleball or something.
That's right.
Or whatever tall Italians do.
Italian.
I think he's Italian. It's a Salvianini machine, and their research center and their top 4 manufacturing sites are all in Italy. So I'm assuming there is a Salvianini US, but I don't think that this is. Thank you. Cool. All right, that's break time.
Actually setting it off, 'cause I'm